To determine the effectiveness of an individual ground rod, firstly, measure the resistance. Use a ground resistance tester or multimeter. Connect the positive lead to the ground rod and the negative lead to a known good ground, for example, a copper water pipe. The resistance reading indicates the effectiveness of the ground rod. Secondly, evaluate the reading. An ideal resistance is less than 10 ohms. An acceptable resistance is between 10 and 25 ohms. High resistance more than 25 ohms indicates poor grounding. The recommended number of ohms for ground rods in a residential setting is 10 ohms or less. For commercial applications, it should be 5 ohms or less. In industrial settings, aim for 1 ohm or less. Note that the required resistance value may vary depending on local codes and standards. It is recommended to consult with a qualified electrician or follow the manufacturer's specifications. Factors affecting ground rod effectiveness include soil conditions, such as moisture and conductivity, rod length and diameter, depth of installation, and the number of rods installed in parallel. Additional tips for improving ground rod effectiveness include using multiple ground rods driven in parallel to reduce resistance, installing ground rods in areas with high moisture content or conductive soil, using longer and thicker ground rods for lower resistance, connecting the ground rod to a ground bus or copper bonding network to distribute the ground potential, and regularly inspecting and maintaining the ground rod for corrosion or damage. The measurement of ground resistance is critical to ensure the safety and proper functioning of electrical systems. Low ground resistance provides a path for fault current to safely return to the source, tripping circuit breakers or fuses and preventing electrical shock hazards. Several methods can be used to measure ground resistance, with the most common being the fall-off potential method and the clamp-on method. The fall-off potential method involves driving two auxiliary ground electrodes into the soil at specific distances from the ground rod being tested. A ground resistance tester is then used to inject a test current between the ground rod and one of the auxiliary electrodes, while measuring the voltage drop between the ground rod and the other auxiliary electrode. The ground resistance is calculated using Ohm's law by dividing the voltage drop by the test current. This method provides an accurate measurement of the ground resistance, but it requires sufficient space to drive the auxiliary electrodes and can be time-consuming. The clamp-on method, also known as the stakeless method, uses a specialized clamp-on meter that induces a test current into the ground loop and measures the resulting current flow. This method does not require auxiliary electrodes and can be performed quickly and easily. However, it is less accurate than the fall-off potential method and is only suitable for measuring the ground resistance of a complete ground loop, not an individual ground rod. When interpreting ground resistance measurements, it is important to consider the specific requirements of the application. For example, the National Electrical Code or NEC specifies that the ground resistance for a single ground rod should not exceed 25 ohms. If the resistance exceeds this value, additional ground rods must be installed in parallel to reduce the overall resistance. In addition to meeting regulatory requirements, maintaining low ground resistance is essential for protecting sensitive electronic equipment from damage caused by voltage surges and transits. A well-grounded system provides a low impedance path for these surges to dissipate, preventing them from reaching sensitive equipment and causing damage. Regular testing and maintenance of ground rods are crucial to ensure their continued effectiveness. Ground rods can corrode over time, especially in harsh soil conditions, leading to increased resistance and reduced performance. Visual inspection should be performed regularly to check for signs of corrosion or damage. Ground resistance measurements should also be taken periodically to verify that the ground rods are still meeting the required resistance values. If corrosion or damage is detected, or if the resistance exceeds the acceptable limit, the ground rod should be replaced or supplemented with additional rods. Proper grounding is an essential component of any electrical system, and regular testing and maintenance of ground rods are critical to ensure safety and reliability. By following the guidelines and recommendations outlined in this discussion, you can effectively measure ground resistance, identify potential problems, and take corrective actions to maintain a safe and well-grounded electrical system. Remember to always consult with a qualified electrician or electrical engineer for specific guidance and assistance with grounding system design and maintenance. The effectiveness of a ground rod is determined by its ability to provide a low impedance path for fault currents to return to the source. A lower resistance value indicates a more effective ground rod, as it allows fault currents to flow more easily, tripping circuit breakers or fuses and minimizing the risk of electrical shock. Several factors influence the resistance of a ground rod, including the soil conditions, the length and diameter of the rod, and the depth of installation. Soil conditions play a significant role in determining the resistance of a ground rod. Soils with high moisture content and conductivity, such as clay or loam, tend to have lower resistance than dry, sandy soils. The presence of salts and minerals in the soil can also affect its conductivity and resistance. The length and diameter of the ground rod also affect its resistance. Longer and thicker rods have a larger surface area in contact with the soil, which reduces the resistance. The depth of installation is another important factor. Ground rods should be driven deep enough to reach moist soil, as moisture is essential for conductivity. The NEC requires that ground rods be driven at least 8 feet into the ground, but deeper installations may be necessary in areas with dry or rocky soil. In addition to these factors, the number of ground rods installed in parallel can also affect the overall ground resistance. Installing multiple ground rods in parallel reduces the overall resistance by providing multiple paths for fault currents to flow. The NEC requires that a minimum of 2 ground rods be installed if a single rod does not meet the 25 ohm resistance requirement. To improve the effectiveness of a ground rod, several steps can be taken. Firstly, ensure that the ground rod is installed in an area with high moisture content or conductive soil. If the soil is dry or sandy, consider adding water or a soil-enhancing compound to improve its conductivity. Secondly, use a longer and thicker ground rod to increase the surface area in contact with the soil. Thirdly, drive the ground rod deep enough to reach moist soil. Fourthly, install multiple ground rods in parallel to reduce the overall resistance. Fifthly, connect the ground rod to a ground bus or copper bonding network to distribute the ground potential. Sixthly, regularly inspect and maintain the ground rod for corrosion or damage. Corrosion can increase the resistance of the ground rod, so it is important to protect it from moisture and other corrosive elements. In addition to these practical tips, it is also important to consult with a qualified electrician or electrical engineer for specific guidance and assistance with grounding system design and maintenance. A professional can assess the specific conditions of your site and recommend the most appropriate grounding solutions to ensure safety and compliance with electrical codes. The use of ground rods is a fundamental aspect of electrical safety. Grounding provides a low impedance path for fault currents, protecting people and equipment from electrical shock hazards. By understanding the factors that affect ground rod effectiveness and taking steps to improve their performance, you can ensure a safe and reliable electrical system. The NEC provides detailed requirements for grounding and bonding, including specifications for ground rod size, material, and installation. It is important to be familiar with these requirements and to follow them carefully when designing and installing a grounding system. Regular inspections and testing of grounding systems are also essential to ensure their continued effectiveness. Ground resistance measurements should be taken periodically to verify that the ground rods are still meeting the required resistance values. If the resistance exceeds the acceptable limit, corrective actions should be taken to improve the grounding system. In addition to ground rods, other grounding methods may be used, such as ground plates, ground rings, and concrete encased electrodes. The choice of grounding method depends on the specific conditions of the site and the requirements of the electrical system. Regardless of the grounding method used, it is important to ensure that the grounding system is properly designed, installed, and maintained to provide a safe and reliable electrical system. The effectiveness of a grounding system is not only determined by the ground resistance, but also by the impedance of the grounding conductors. Impedance is the total opposition to current flow, including resistance and reactance. Reactance is caused by inductance and capacitance in the grounding conductors. High impedance can limit the flow of fault current, reducing the effectiveness of the grounding system. To minimize impedance, grounding conductors should be as short and straight as possible. Sharp bends and long runs of grounding conductors can increase inductance and impedance. The grounding conductor should also be sized appropriately to carry the maximum fault current. The NEC specifies the minimum size of grounding conductors based on the size of the overcurrent protection device. Proper bonding is also essential for a safe and effective grounding system. Bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Bonding helps to equalize the potential between different metallic parts, reducing the risk of electrical shock. The NEC requires that all metallic parts of an electrical system, including equipment enclosures, conduit, and piping, be bonded together. Bonding conductors should be sized appropriately to carry the maximum fault current. In addition to grounding and bonding, surge protection is also an important aspect of electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning, switching transients, and other sources. SPD diverts surge current to ground, preventing it from reaching sensitive equipment. SPD should be installed at the service entrance and at sensitive equipment locations. The selection of SPD should be based on the specific voltage and current requirements of the equipment being protected. Regular testing and maintenance of SPD are also essential to ensure their continued effectiveness. The overall goal of electrical safety is to protect people and equipment from electrical hazards. Grounding, bonding, and surge protection are all important components of a comprehensive electrical safety program. By following the requirements of the NEC and other applicable standards, and by implementing best practices for electrical safety, you can create a safe and reliable electrical system. The information provided here is intended for general guidance only and should not be considered a substitute for professional electrical engineering advice. Always consult with a qualified electrician or electrical engineer for specific guidance and assistance with the electrical system design, installation, and maintenance. The NEC is a comprehensive set of standards for electrical safety, and it is essential to be familiar with its requirements. The NEC is updated every 3 years, so it is important to stay current with the latest edition. The NEC covers a wide range of topics, including grounding, bonding, wiring methods, overcurrent protection, and equipment installation. The NEC is enforced by local authorities, and it is important to comply with its requirements to ensure the safety of people and property. In addition to the NEC, other applicable standards may also apply, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is important to be familiar with all applicable standards and to follow them carefully when designing and installing an electrical system. Electrical safety is a shared responsibility, and everyone has a role to play in preventing electrical accidents. By following safe work practices, using appropriate personal protective equipment, and being aware of potential electrical hazards, you can help to create a safer working environment. If you are not qualified to perform electrical work, do not attempt to do so. Always hire a qualified electrician for any electrical work that needs to be done. Electrical work can be dangerous, and it is important to have the proper training and experience to perform it safely. By taking these precautions, you can help to prevent electrical accidents and ensure the safety of yourself and others. The knowledge shared here provides a solid foundation for understanding the importance of ground rods and their effectiveness in electrical systems. Remember to prioritize safety and consult with qualified professionals for any electrical work.